I bring you Professor Pei.
Thank you for holding, and I appreciate the invitations from Professor Alfred, Professor Gallo, and the committee. Today, my topic name is what understanding the structure and the electron structure of salvage protective data cluster. This is a theoretical studies. First of all, this is my trip from China to Mexico. It's a long trip. I spent about 20 hours. Here, in my university city, Shanghai. Here is Shanghai. So I fly from Shanghai to Shanghai, then Shanghai to Mexico City, and then to Payata. Shanghai City is in the center of China. Okay, this east is central China. This is my university. Shanghai University was advocated by Chai Mao Zedong, the foundation of China, founder of China, and Shanghai City is his hometown. So this university was advocated by him, and now this university is 60 years old. This is the chemical building that where I work. Okay. And this some place in my university, I think. Okay. Today my talk includes two parts. The two parts. The first is about the inherent structure rule of the cell electrode cluster, and the second is about structure evolution map we have recently found for the FCC structured cell electrode cluster. And based on this map, we have summarized general electronic structure relationships for these clusters. Okay, so why we are so interested in the cluster research? Because, you know, in the field of cluster research, the fundamental issue is to understand the atomic structure and their bonding patterns. So since from 1970s, okay, several structure and electronic principles or rules have been proposed based on the studies of different class of clusters, such as carbon borons and this carbon cage family. And this is very popular in the inorganic chemistry. This is a transition metal carbonyl compound. Okay, based on the studies of these clusters, nanoclusters, people have summarized many structure and electronic rules, such as the famous Widow-Nichols rules and this PSEPT theory and this Cotton's bonding theory and so on. From this established cluster structure and electronic rules, one can first understand the bonding nature of the cluster and explain theoretically why they formed such skeletal structures. And more importantly, these rules allowed us to explore and predict some unknown structures. Those clusters have been, for example, some clusters have been synthesized in the lab, but it was hard to determine its atomic structures. So based on these rules, we can explore some unknown structures. Okay, so I think it is very important in the field of nanocluster research to develop the new structure and electronic rules. My research focused on the gold cluster and with the ligand protection. So from this element table, we know these 3D and 4D transition metals, they can easily form some ligand and metal complex. But for the gold, it has fulfilled 5D orbitals and only left one unoccupied 6s orbital. So it is not easy to coordinate with some ligand. And the well-known gold ligand compound was the gold phosphate clusters. This was the first report about in 1960s, and suffers 40 years studies. And in this cluster, gold and phosphine formed a dead bond. This is a top absorption, top side absorption. And another well-known compound is the gold sulfide, but this is less stable. The crystal structure of gold sulfide is here. Each gold was coordinated with 4 silver atoms in the lattice. So here is the examples of the gold phosphine clusters synthesis during past 40 years, around 50 years. There were many examples. These are crystal structures. Okay, from these crystal structures, we found the ligand gold coordination adopted conventional core, bridge, hollow side bonding. So there's no surprise. Why? Because it had a clearly defined interface between metal core and ligand. And we can divide this cluster into a metal core and a ligand. And between metal core and ligand, there is a clearly defined interface. This is very similar to the already known transition metal clusters with ligand. Okay. So, but in 2007 and 2008, there are 2 breakthroughs in determination of the cluster structure of gold and cellulate protect gold cluster, included gold 102 and gold 25. These are the most famous two clusters. Surprisingly, from the crystal structure, okay, we find it can be found that in both clusters, they formed a new kind of ligand motif. Now we know that is called a staple motif because the shape like staples. Okay, this cluster can be divided into a zero valence metal core and a ligand shell contain this AU1, gold 1 atom between 2 cellulose ligand, or between each gold between 2 cellulose ligand. From these cluster structures, we obtain some new insight. We call it divide and protect, because some gold atoms were lifted from the interface to form a new ligand motif. So from these 2 crystal structures, okay, we have 2 questions. The first one is whether or not all these clusters have the same structure pattern. And the second question, what are the underlying structure, electron structure, and the stability relationship? Okay. To answer these questions, for the first one, actually, before 2012, the exact knowledge about the class structure is very lack. Only 3 cluster crystal structures were available before 2012. And for the theoretical studies, I'm in theoretical studies, so we know that there is lack of efficient structure search method for this complicated ligand protected gold cluster, largely because the freedom of ligand. So there are some well-known structure search methods for the atomic clusters, such as gene method, simulating annealing and beta holding, and so on. This method work very well for the atomic cluster without ligand, but these methods are very hard to predict the structure of ligand. negative cluster because the complicated ligand combinations. So we need an efficient method to explore these class structures. And for second question, what is the underlying structure electronics structure stability relationship for these classes? Why this question? Because from this mass spectrum, people have found in the one-port synthesis, some clusters exhibited exceptional stabilities. For instance, these clusters are very stable during the one-port synthesis in solution. If we count the electrons numbers of these clusters, for example, for this one, it has 8 electrons. For this one, it has 18 electrons, and 34, 58. Okay, we know these red color electrons are the magic numbers in the spherical gallium models. So this can be used to explain their stabilities. But there is an exception here. Gold 38, it is also a very stable cluster, but it only has 14 electrons. It is not a magic number. Okay. So we started to research these clusters from the structure analysis. From these two, gold 25 and gold 102, we can find that for both clusters, they can be divided into a metal core. This is a zero valence metal core, zero core, and certain numbers of motifs, Okay, based on this structure analysis, we have proposed a general structure formula for stellate protected gold clusters. We propose that for any stellate gold cluster with different compositions, different number of gold atom and stellate ligand, they can all be divided into metal core and certain numbers of motifs. But in the motifs, we added some new motifs. For example, here. These two have been found in gold 25 and gold 102. And these three we added in the formula in this paper. We, according to the number of gold atoms in the motifs, for instance, here is one gold atom, so we call this is level 1 motif, and the level 2 motif, level 3, level 4, level 5, and so on. So we proposed a structure formula. So based on this structure formula, we can devise efficient theoretical method to explore the class structure. So we do not need to consider the ligand effect during the structure search. Why? Because according to the structure formula, we can divide any clusters into a metal core and a certain number of already known motifs. So what we should do is carry out a structure search for the metal core. And after that, we combine these motifs, or we put these motifs on the surface of metal core to assemble a cluster, and then we use DFT calculations to do geometry optimization, and then we rank their energy orders. Okay, this is the first example we used this method. This is about the structure prediction of gold 38. The gold 38 is a famous cluster in this field. It was first synthesis in 1999. And however, after 10 years, it was first synthesis. The structure was totally unknown from both experiments and theory. And here, there are several theoretical works to search its structures. One work was from Gallup, Professor Gallup, in 2000. Okay. However, for all these structure models obtained from theoretical methods, they do not agree very well with experiment measurement. So with our proposed method, we can predict structure by a simple way. We only need to firstly we can divide the cluster into metal core and ligand shell. Okay, we find that there are only 5 possible formulas for the gold 38, and so it can only have 5 gold cores, 5 types gold cores. So what we needed to do is to search the structure of 5 cores, 5 gold cores. Finally, we obtained this core. This gold core is made of 2 X features, and the 2 X features share a triangle face. They share a triangle face. The total number of this gold core is the total gold atom in this gold core is 23. Okay, we found that this structure model is very stable because it has very low electron energy. It is given about 2.06 eV, lower than the next one predicted during the last 10 years. And to confirm our theoretical predictions, we have carried out TDFT calculations to study the UV-VS spectrum. This spectrum is available for the experimental studies, so we can compare directly the theoretical prediction and the experimental findings. Here, the black curve is the experimental curve. This is experimental curve, and the blue curve is from the theoretical models. We can see here the optical gap. Experimental value is 0.9 eV, and the theoretical value is 0.89 eV. I agree very well. And this peak and this peak fit very well with the experimental curve, but only here. The theoretical model predicts 2 peaks here, but the experimental curve only has 1 peak here. And the right one is a comparison of powder X-ray curves. Black line is the experimental one, and this is the theoretical predictions. Okay. So after 2 years, we report the class structures. Here, I need to mention that in my predictions, I made there is drawback. We wrongly predict the orientation of the ligand orientations. We predict that the whole class is a C3V symmetry, but actually it is a D3 symmetry. Okay, the ligand rotates for 30 degrees. Rotate. And the experimental crystal structure was reported by Professor Jin in 2010. And we can see our theoretical model agree very well with the experimental crystal structure. Okay, this is the first example. And in 2012, we predict the class structure of gold 24. This class was synthesized in 2010. And here is the comparison of the UV-VS spectrum predicted from theory and the experiment. And the right is the powder X-ray diffractions curves. But unfortunately, there is a surprise. After our theoretical works, there are 2 experimental crystal structures. The difference is, we can see this one, what we reported in Professor Zhu's group in China. He found that when the ligand is SER rather than SR, the crystal structure agree very well with our theoretical predictions. But when the ligand was switched to SR, not SER, SR, so the structure is different, slightly different. So we don't understand why. Because we know SE and S, they are in the same group, right, in the element table. But they totally have much different structures, crystal structure. Okay. Then in a later theoretical work carried out by Professor Zhang in USA, he found that the effect of ligand interactions played a vital role for the stable structures. For these two clusters, they can be built as a pair of isomers. But if we change the substituted group, for example, here the R is CH2pH, the cluster favors these isomer structures. But if we change the R to CH2pH TBU, this structure becomes more stable. So these DFT calculations indicated that the ligand, especially the steric effect of the organic substituted group is very important for determination of the stable class structures. Okay. Almost at the same time, Professor Jin, he reported 3 crystal structures used different by changing the SR ligand. Surprisingly, we found that these 3 clusters, this goes 23, this goes 28, 36. These 3 clusters had FCC course. So let's see. You know, for the barcode, it is well known the barcode in FCC structure. Okay. I remember yesterday someone asked the Professor Jin, is the FCC structure stable in the ultra small nanoparticles? Yes, almost we answered no. But this is a surprise because with the ligand protections, the gold may be stabilized in the FCC structure, even at a very small size. For example, 28 and 36 and 23 even. So usually we know the evolution of ligand and gold cluster. They take co-share groups gradually through the shell off shell, and they form a class of back-hedger forks. But this is the first time we find the FCC structures. These 3 examples. So at this time, we think this experimental determining the FCC structure clusters, ultra small clusters, implies there is an alternative nucleation group pattern other than the co-share groups, and there is a new electron structure stability effect other than the spherical Galilean model. Why? Because according to the spherical Galilean model, the metal core must be a spherical shape when its total electron number is magic number, for example, 8 electrons. When for gold 25, it has 8 electrons. So the gold core is a spherical shape. But for this one, it is an isoelectronic cluster. It also has 8 electrons, but the gold core is non-spherical. Okay. So with this knowledge, we carry out structure division for gold 44. This part was first reported by Professor Witten in 2005, and lately it was also detected in later synthesis. But for a long time, its structure is unknown. And using our method, finally, we obtained a half-stable class structure here. Surprisingly, it's also an FCC structure. It is also an FCC structure. But one thing is different from experiment, like when we use the dianion state, when we use either two electrons to the cluster, the spectrum calculated from TPDFT is much different from the experiment curve. Here is the experiment curve. Here is the TPDFT results. So we can see from the experiment curve, the optical gap is about 2.5 dB, but the TPDFT predicted a very small optical gap, about only 0.4 dB. So we solved this issue for a long time, and finally, we think this cluster may be a neutral charge state and not ionic state. So we recalculated the spectrum using TPDFT based on the neutral charge state. Okay, the things was changed. That the spectrum fit very well with the experiment one. So we propose this cluster is a neutral cluster, and this model might be a very good candidate structure model. Okay, at the same time, Professor Jin, they also obtained the similar conclusion. This is a mass spectrum confirmation of the charge state of this cluster called 44. And another thing we find from this cluster structure is that we find that this code 44, the structure we predicted, and we found that the predict structure code 44, it had a very good relationship to two previously clusters, reported clusters, for example, 28, 26. You can see from 28, go to 28, when we add go to 8, SR4, we reach go to 26. And then we add another unit, the same unit, we go to 44. If we continue to add this unit, we will go to a series of clusters. This is a homogeneous cluster series. Okay. And it has a popular formula here, with n is 1, 2, 3, 4, 5, and so on. So in 2016, Professor Jin successfully developed two class structures. This is code 44. This is code 52. Okay, and we can see here is 28, 36, 44, and 52. And this cluster series, okay, this cluster arrays agree with this evolution trend. And we have compared our select models with the experimental one. And we find our select models agree very well with the experimental finding. We did not consider the ligand. We simplified the ligand to massive group. Okay, with this knowledge, we further consider since these four have been reported by experiments. So what about these last ones? Here, 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 and here. In 2015, a group from Japan, they reported the synthesis of a ceramic protected gold cluster with a formula of gold 76 and SR44. Oh, we find that this cluster satisfies very well with this homogeneous cluster array here with N is 7 and is 7. So we can easily obtain its cluster structure from theory. Then we did carry out theoretical calculations. Here is a structure model, and the right one is a comparison of the experimental optical curve and the TT-DFT results here. We can see the future peaks here, and here, all agree very well, and with the all the accurate curves. Okay. And recently, we also devoted our studies to the 14K solid Dalton format species. This is a favorite class species because from this picture, the mass spectrum go to 25, go to 38, go to 44, and go to 102. All of them have been dissolved by the single crystal. All structures of this cluster have been dissolved, but only this one is unknown. And for this one, different groups predict different molecular formulas. For instance, here is the 68, 34, and then they slightly modified to 67, 35, and in 2014, 68, 32 was reported. So there are still some debates about the exact molecular formulas of this species. From the theoretical view, we predict a new species with valence electron structures. For the left one, we can see the two electron units here, take a zigzag arrangement. So the linear combination of this molecular orbital finally led to a ES, EP, and ED orbital rather than EP. We know the orbitals or atomic orbital. We know that is the order is ES. Is SP, 1s3p, and here is 1s2p, and then jump to D. But for this one, it's a spherical one. It has a spherical shape. Okay, you can see it's a regular electron configuration. It's a ES3p, S3p, but this one is S2p and 2D. These two both have 8 electrons. And finally, we think the most important thing from this map is that we can predict new species. So this one, gold 15 as a term, we can derive its structure from the evolution line. And recently, my collaborator, Professor Zhu, they have obtained the crystal structure of this cluster. So the experiment and the theory agree very well in the structure. In summary, we have proposed a genetic structure rule for the 7 protectable clusters. And with the aid of these theoretical simulations, it is possible to accurately predict some unknown class structures. And finally, from this year's effort, we have established a genetic topological structure and the electron structure and the electronic structure relationship for these clusters. And I'd like to appreciate the NSFC from China and my collaborators, this experimental group leader of the experiment group, Professor Zhou Zhu, and I'm with University of China. And this is my research group members. And this is the first Dr. Ma. He is here, come with me. 15 students and one postdoc. Thank you very much.
Thank you, Professor Pei. This paper is now open for discussion, questions, comments, compliments. Yes.
Thanks for a very beautiful talk. I have one question and another thing. So the first one is if you can also use these kind of models to predict beyond the clusters the nucleation and growth of nanoparticles, which is your view on it. Is it so complex? Is it feasible?
This model can be only used to this kind of cluster, because our method is based on the structure rule. So the structure rule is only validated in this class family, not for others.
And the second one, okay. You obtain the electronic states of the cluster, then you can do the optics.
Yeah.
Do you have any information on the magnetic properties of these clusters? Can you extract any magnetic information about them?
Magnetic?
Yes.
No. Gold can, so this cluster, they have the closed shell electrons. Okay, no magnetic. Okay. No magnetic properties.
No, and just a curiosity, no magnetic properties have been observed for this kind of cluster.
Yes. No problem. Okay. Thank you.
Thank you, very illustrative talk. You show a lot of results, very high quality results. So I have first general question is after doing all these kind of calculations and obtaining such interesting results, what do you think is the real role of the ligand shell with respect to the metallic core? Because you know that there is a lot of information on the structures for virtuous in the case of gold and silver. But what is happening is that the structure of the metal core is different than the structure of the virtuous for the same size. For example, in gold 25, the core is an icosahedron, perfect icosahedron, kilograms. But then the atom cluster with 13 atoms is I think, planar or with a bilayer structure. So you really think that these are two different chemical or physical systems that with no relation between them? Or at some point the ligand shell should be irrelevant for the structure? But in this size range, it's not yet happening. So, what is your opinion on this in general terms? That is one general question. And the other one, a specific question, is in the case of this series of clusters in which the last two are 144 and 152 with these special ligands. You think this very nice structure. Yeah. But I remember in your papers, you also discussed the structure as the existence of two helical patterns.
I didn't.
But you, in this talk and in the previous talk I heard from you, you didn't put emphasis in that pattern. So I'm asking why you don't mention anymore this helical structure.
I think I mentioned that.
Yes.
Thank you. For the first question, quite an important question here. Actually, the ligand, I mentioned here, the ligand is very important to define the stable structures. Okay, and without ligand, in the size of a few tens to atoms, for example, people 13, it's a plane structure without ligand. Okay, it's a plane structure, and then it goes to two-dimensional and to three-dimensional. Okay, but when the ligand is added, yeah, I think these are chemical interactions. I don't know the from the chemical view, the gold has 5d 6s1 electron. Okay, when there is no ligand, the bonding between the gold atoms, they tend to, okay, I think, I can't express. But here I can only say that for most ligand protected metal clusters, the core is always shaped, always spherical shape, non-planar, and much different from the ligand-free system. Okay. But I think the nature is the electron interactions between metal atoms and between metal and ligands. And for these clusters, as you said, the type of SR ligand is very important for both stable the structure and crystallization. For some, we know in several syntheses, they can detect the signal of cluster, but they cannot isolate or purify or crystallization because maybe the cluster is less stable. But lately they can Professor Jim reported a lot of state structures from the crystallization by crystallization. I think because the stabilization effect of the liquid shell. The liquid shell has a stronger stabilization effect on the metals. It can also tune the structure or change the structure of metals. But in our simulations, we did not consider the realistic ligand. The real ligand we didn't consider. We always use the method group because we find that the spectrum is less sensitive to the ligand type. So we use the method group for all calculations. Sometimes we use the real ligand, sometimes with.
Thank you. Other questions? Yes, Professor Miller.
Very nice. I have one question about the relative stability of the different clusters. There are cases in which you can transform a stable cluster into another cluster.
Yeah.
So without addition of ions, nothing. Like you reported very recently, the spontaneous transformation of those 25 into 38.
Yeah.
Just with temperature.
Just with temperature.
Yes. So that means that there has to be a relative, you're talking about the relative minimum. These stable clusters to be transformed into others. And do you think that your methodology you could predict some spontaneous transformation?
Which high? Too high. because it's a dynamic process. From the current select models, we cannot use. We we have tried this. No success.
Okay, but you can still do the thermodynamics.
Yeah, but that is very hard. Too
Computational or computational too cost.
How large can you go with these methods? Can you predict the structure with 60 ligands? Magic number 60?
No, actually, some works I did mention in this PPT, and this is our recent work. We did a structure search between 100 to 150. Okay, between 100 to 150, we carried out. I did not mention this paper.
Yeah, I don't see 60.
Or 60.
60 ligands.
6 ligands. Okay. It does not list here.
Maybe it's preprint. Maybe it's will be published soon by you.
It has been published on that scale. This year.
Okay, published. Not it. Yes, one more brief question.
Thanks, guys. Very nice work. I just find it interesting you talk about nucleation and growth.
Yeah.
And you were able to predict the small unit in terms of nucleation.
Yeah.
You also talk about growth to 1D, 2D, 3D. I'm wondering if this calculation can also predict whether this 1D growth is through certain kind of aggregation or two small units to aggregate, or like yesterday, how we were talking about diamond, triangle, you know, so, or just during the atoms adding to this initial nucleus, you know, what's the comments about the possibilities?
Yes, actually, we have reached unified models basically, but because it is still in preparation, so I did not I did not talk here. Using our unified model, we can expand all axis structure. There are nucleation groups, pathways, and why, and explain why these structures. I will publish.
So in preparation.
Yeah.
All right. Thank you.
Well, the time that's being the organizers have asked me to make an announcement this afternoon. The talk scheduled by Luciana Schmidt, Dr. Schmidt from Cordoba. She will be speaking in Friday.